This tape demonstrates some of the techniques developed for using shadows and mirrors to visualize and manipulate 3D objects. The opaque silhouette shadow helps the user determine where an object is actually located relative to other objects in 3-space. In this segment, the user directly manipulates a propeller and checks his progress by monitoring how the propeller lines up in the 3 shadow views. The shape of the silhouette provides the perceptual cue needed to correlate the shadow with the 3-dimensional object. In order to avoid problems with occlusion that sometimes occur with silhouette rendering, we now show an example with wireframe shadows. The wireframe shadows resemble 3 orthographic views of the scene. In fact, the shadows can be manipulated as if they were traditional orthographic views. The user is able to line up the propeller with the airplane by translating it first in the bottom view until the shadows are aligned, and then by translating it in the rear view until those shadows are aligned as well. The wireframe rendering makes the propeller's alignment with the plane easier to identify. In addition to facilitating the constrained translation and alignment of objects, shadows can be used to perform constrained rotations on objects as well. Here the plane is rotated about each of the world's principal axes. The more detailed rendering of the shadows allows the user to better perceive the effect of the constrained rotation upon the object in 3-space. This view is similar to a mirror in the sense that the object appears as a reflection, but is different in the sense that the reflection does not change with the viewing angle. This next segment shows a common technique for snapping 2 objects together. We first choose a point on the surface of the landing gear that we want to attach to the plane. Then, by manipulating the camera, we find the point on the surface of the plane that we want to snap to. The difficulty here is that we would have to change the camera again to snap the rest of the gears. Another way to achieve the same snapping effect is to rotate one of the objects so that both snapping surfaces are visible. The user rotates the plane so that the destination surface can be seen, then a point on the landing gear is selected, and a snap to the now visible underside of the plane. Since we had to modify our model, the invariants required by our naive implementation of snapping have been broken, and the landing gear is misaligned. Shadows provide a better mechanism for performing the snapping operation efficiently. We add a mirror to the shadow views so that all object selections with the mouse are reflected onto the 3D object. The user can now pipeline the process of snapping by beginning subsequent actions without waiting for previous actions to complete. This is because the mirrors have made it possible to see all snapping surfaces without the need to perform any intermediate modifications to either the camera or the objects in the scene.
The deformation operators are powerful high-level tools for manipulating the geometry of objects. However, users struggled to control as many as 14 different parameters in this 2D array of sliders. These one-dimensional sliders have a number of disadvantages. First, they consume a great deal of screen real estate. Second, they artificially separate related parameters from each other, such as the 3 components of a vector or point. Lastly, they remove all controls for parameters from the 3D view of the object, increasing the distance between user intention and their actual effects. We can see how difficult it is here to relate the positions of the sliders to the actual deformations performed on the object. A 3D direct manipulation interface can be developed for deformations. However, this kind of interface must fix most of the parameters of the deformation and map mouse gestures to the 1 or 2 remaining values. Here, the mouse gesture controls the twist angle of a deformed cube. Unfortunately, like the gestural techniques for transforming objects described earlier, this interface does not display its affordances, and there is no feedback beyond the visible twisting of the object. Since 2D widgets and 3D direct manipulation are inadequate controls for such an inherently complex 3-dimensional operation, we introduce a rack into the 3D environment which directly modifies parameters of the twist deformation. The upright bars of the rack control the amount that each end of the object is twisted, as well as the range of the operation.